For Module 2, Homework 3, we're going to stop talking about linear equations or straight lines, and we're going to start looking at these graphed lines that we have as relationships. A relation of a set of ordered pairs of real numbers is really every number that's represented by a point or a coordinate on the line. So we can look at these two different ways. We're going to start thinking about the domain. And the domain, we sometimes just abbreviate that as D, is really the set of all the first coordinates in the relation. Those are all the x values, if you will. And the range is the next one. And that is a relation of all of the second coordinates in the relationship, and that's going to be, or the relation, and that's going to be the y values. So when we have a set of points, as we do when we have any kind of linear relationship or linear equation, then we've got a relation. We've got a domain, and we've got a range, domain being all the x values, the range being all the y values, and then we can further define this as a function. Now, sometimes these linear, these relations that we have are functions, and sometimes we'll say they're not. But a function is a relation in which each domain element has exactly one corresponding range element. In other words, you can think of it this way. For each x value, each x coordinate, you will have only one y coordinate. Now, the reverse of that is not true. For each y, you might have multiple x's. But the way we're looking at it, for it to be a function, every x, individual value for x, each domain element can only have one corresponding range or y element. Now, that gets a little bit confusing. So I'm going to look at it several different ways in each of these examples. And I'm going to be saying the same thing several different ways. So just bear with me here. As we go through example 1, we're going to look for the domain and the range of each of these relations. Now we've got a set of points here, the x and the y coordinates of these set of points. And we're going to be able to tell when we finish whether this relation is a function or not. So the first point is x of 1, y of 6. So we say it has a domain of 1. The second one has a domain of 2. I'm just going to separate them with commas. The third point has a domain of 0. And the fourth point has another domain of 0. So I've got the 4 domains, the 4 x values for my 4 points in my relation. Now I'm going to look at the corresponding y, or the range, and that would be for the first one, for that 1, it had a range of 6. For the x of 2, we have a y, or a range of 8. And for the 0, x of 0, well, we had a 3, and we also had a negative 2. That's going to it's going to help us define whether or not this is a function or not. Now, what do we see? Well, what we're saying is that anytime, this is an equation, that anytime you input a 1 for the value for x, you will get a value of 6 for y. Anytime you input a 2, you're going to get an 8 for y. But what happens when you input a 0? Well, that's where it's really coming out not looking clear to us. So let's go and look at it another way. Let's take our x's and y's and put them in a table. I had 1, 2 was the first point. Well, sorry, 1, 6. And the next one I have is 2, 8. And then I had 0, 3 and 0, negative 2. Okay, so I have an x of 1. That's my input, and what happens when I input an x of 1, when I substitute in 1 for the value of x in this equation, well, I got an output, or a y value of 6. Same thing happens, I have a 1-to-1 relationship when I get a 2 and I output an 8, but when I input a 0 for x, I might get a 3, or I might get a negative 2. And that means I do not have a function. Remember, for each x value, I can only have one unique y value. And this one, for an input of 0 for x, I get a possibility of 2 different ones. So we would say for this one, what is the question to? Is it a function? It is not a function. How would we graph it? Well, let's look at what it looks like here and just graph these 4 points, okay? I've got 1, 6. I'm going to go over 1, x value 1, positive 6. There's my 1, 6. Let's do 2, 8. 2, and here's 8. And let's look at 0, 3. 0, 3 would be right here, and the next point was 0, -2, which is 0, -2. And you can see that these two are my problem. These two line up directly on top of each other. In other words, that means they have the same x-coordinate. If something in a set of points has the same x-coordinate, different y's, it is not a function. That would help you define it. Now let's look at B and go through this again. We've got a -1 is my domain for the first point, and I had a range of 8. I'll go ahead and write it down. The second point is 5, 8. Well, the x value, or the domain value, is 5, range of 8. I've got a -1 here for x and a +2 for y, a -7 for the last one, and a -9. Those are the 4 points in this particular relation. So now I'm going to write them in my chart because I just am looking at it all different ways so that I can make sure you understand it. If I have an x value of -1, the first point had a y of 5. Then I'm sorry, I'm doing that again. 8, sorry guys. And the next one I had x of 5 and I had a y of 8. And the next point I have a x of -1, a y of 2, and the last one I have an x of -7 and a y of -9. I think I got all those right. Now, let's look at that with our little input and output chart. When I have a -1, I get an 8. When I have a 5 for x, I get an 8 for y. Well, that's the same point. That doesn't matter though, right? It's just has to be, each x has to have an individual, has to have only one y. But I have individual x's here with just one y, don't I? So let's look at the next point. It's a -1, 2, and the last one is a -7, -9. Now, how can I tell if this thing is a function or not? Well, okay, I'm beginning to think it might have a problem. For a -1, I have an output of 8. I also have the same thing down here, don't I? An output of 2. Well, that's the same x-coordinate. If I hadn't written that one down, you'd see I had one x-coordinate with 2 different y's, didn't I? For 5, I'm always going to get an 8. That one's okay, even though there is an 8 possibility for an x value of -1 also. That one doesn't bother my function possibility being function, but -7 and -9 are okay. Let's line it up on our chart and see if we can look at it vertically or look at it graphically and see if it makes sense. When I have a -1 and a +8, the point would be right here. When I have a +5 and a +8, well, that point's going to be right there. When I have a -1, I would have here is a +2, and then I had another point that was a -7 and a -9. Now, where's my problem? Right here. Once again, these 2 points are stacked on top of each other, and that means that they have the same x value, and each x value has to have a unique y value in this one, and that's going to cause me, or it's going to cause me trouble, and it's not going to be a function. So this one we could say is also not a function. Now, I'm setting you up for something that we're going to talk about on the next page called the vertical line test. You can tell if things are a function if you can graph them, and if you can draw a line straight up and down anywhere in the graph and it hits the point or the line more than one time, it's not a function. Let's take a look at this on page 17 here. See if it makes sense to you. The vertical line test says that if you have a vertical line intersecting the graph and it hits that graph or that particular line at more than one point, then it is not a function. For example 2a, we look at this, really it's a linear equation here. It's a straight line, isn't it? And I can draw a vertical line anywhere along this line. It's only going to intersect it one time. So is this a function or not? Yeah, by the vertical line test, this one's a function. For every value of x, I do have a unique value. I have just one y value. I have a unique y. And that's my vertical line check, isn't it? Okay, so let's look at B. This one, now this, although this looks like it's going to start going straight up, it's not. It's still slanted slightly, so it's going to go all the way to infinity. This thing will go, well, if we continued it, it would go all the way to negative infinity. This one would go all the way to positive infinity, because although it's going to be going really, really high, it's still also going either to the left or to the right. Just a little bit, but that's enough. So this is going to be straight up and down lines, vertical lines drawn anywhere across it, is only going to cross this particular graph at one point. This one would also be considered a function. You can do your vertical line test and see. What about C? Take a look at C with me. Now C stops at a x value of 1, doesn't it? But it goes all the way to positive infinity, because you can just point an arrow. This keeps going to positive infinity and to positive infinity, this one. But if I drew a vertical line anywhere along this graph, I would cross it at 2 places. So this one is not a function. And as you've probably already guessed, neither is a circle. A circle really can't ever be a function, can it? Because anywhere I can choose to draw a vertical line, it's going to hit it at more than one place. If I can do that, if I can do it just once, it's not a function. I can do this one many times, can't I? So there's your several ways of looking at whether things are or are not a function. And the best way we have found is this vertical line test. It's the most graphic way. It's the best way for us to remember what makes a function and what does not. Let's take a look at some more examples. They've asked us this time to do more than just see if it's a function or not. They've asked us to actually identify what is the domain and what is the range of each of these relations. Now remember, the domain is the range is the values of x. The range is the possible values of y. We're going to use the vertical line test to tell whether each graph is a function or is not a function. And we would look at the first one and say, well, I can draw a straight line, a vertical line, in many places, and it would cross it more than once, so it is not a function. I'll get that part out of the way. I've identified this first one as not a function. Now they've asked, what is the domain? To answer that question, we have to say what values could be for values of x in this particular graph. Well, the smallest x can ever be, over here on the far left, is -4. It stops at -4. It never goes any further than that. So it goes from -4, and I'll put a comma to see how far does it go to the right. Well, it stops at +4. So my domain would be from -4 to +4. What about my range? Well, let's see, how small does it ever go? It's in a negative direction on the range, or the y-axis is down, so I go down to a -2. And the smallest this one's ever going to get is a -2. I go back up to see what the biggest it'll ever get to, and I come to a +2. So my domain is going to be -4 to +4. My range is -2 to +2. And it is, of course, not a function. Any kind of elliptical, circle, anything that overlaps itself can't be a function. For example B, you just have to remember what I've told you. These lines are pointing slightly out. So you have to imagine that they're never going to turn and go straight up. They're always going to be going slightly, slightly, slightly to the left, this one is, and slightly to the right. So this one is going to go all the way to -infinity, and this one is going to go all the way to +infinity, right, in a domain direction. In other words, if I was thinking, how far to the right is it going to go? Well, it's going to go forever to the right, isn't it? How far to the left is it going to go? Well, it's going to keep on going to the left a little bit at a time until it reaches -infinity. That is my domain. It'll go from -infinity on the left to +infinity on the right. Now, I know this looks like this line was going up, but that does tell us, now we can start looking at how high does it go and how low does it go. Well, the lowest it ever goes is going to be -4. That's going to be the bottom end of my range. How high it goes, well, it's going to go up until it reaches, it has nothing to do with these left and right infinities, but straight up is +infinity on the y-axis. So it's also going to reach infinity, +infinity on the range. The domain, it's going to cover every single part of this number line from negative infinity to positive. But on the range, it doesn't go any further, any lower than -4. So can I call this a function? Well, if you draw a vertical line anywhere across it, it will only cross it once. So this one, yes, is a function. Now C is a strange looking little graph. We won't graph these much. We'll talk about them more in the next class. But is this a function or not? Now, I would go ahead and say vertical line test. I'm thinking anywhere I can draw a vertical line, it's only going to cross it once. So C is a function. Looks like it to me. And then I want to know the domain and the range. I want to know how far it goes left and right and how far it goes up and down. Well, the domain is, once again, keeps on going to the left, doesn't it? Keeps on going to the right. So I've got another negative infinity to positive infinity domain. The range, however, is never going to go any lower than a -2. That's my smallest range, but it will go continuously in an upward direction, so eventually it will reach toward infinity. Now let's look at this next set of points here, this relation. And it's a little strange to us, but it is a slanted line. It's just going to stop. It has a stopping point on each side, doesn't it? It's not like these others that we could literally say these are arrows. They go on forever and ever. And this one has a point where it stops on each end. And it also has a point where it makes an abrupt turn. Is it a function? Well, I would do the vertical line test and say, even though that comes close to being a straight up and down line, I know it's not. As long as it's not a straight up and down line anywhere, it passes my vertical line test. It will not cross itself. It will not hit in two places. You have to think theoretically on this because I know you can't draw a line fine enough for that to happen. Now let's look at the domain. How far to the left does it go? Well, the smallest I go here is right here, this point, which happens to be -1 on the x-axis. And that would be the smallest my domain reached. And how far do we go to the right? Well, the furthest to the right I got was a +2. So that's my domain, -1 to +2. As far as the range, I go down here and I say, what's the lowest it gets? Well, it goes down to a -2. And it stops at a +9. So my domain, -1 to 2. My range, -2 to 9. Now let's look at the next page and start talking about function notation, because we did all this, or talked about functions just so that really we could be thinking of our equations as functions and be learning some new terminology that we're going to use more in the next class than this one. So we want to look at a function as it's a sorry, it's a function of x, and it's considered y is the function of x. We write an equation, y is equal to the function of x. Now, so instead of writing y, we can write the term f of x, function of x. And that's just function notation. F is the same as the name of the function. In other words, we've named this function f. And f of 4 means that every x value in this function, we would replace it with a number 4. And then we would solve it for f of x, which would be actually y. So just to kind of look at it like this, anytime you see g of x, you're thinking the name of the function is g, and g of x, you can sort of think, well, that's y is equal to, okay? So anytime you see function notation, you can sort of in your head substitute y. So g of x is equal to 2x squared plus 3, and we want to find what is g of -2. Well, that's saying what is y when x is -2? That's what the question is. You can write that down if you want to refer back to it. What is y when x is equal to -2? That's g of -2. You want to find it. So you say g of -2 says take this equation and substitute -2 in for every x. Now don't forget, when you have a negative and you've got it raised to an exponent, you are raising the negative to the exponent, and you have to say -2 times -2. In other words, this one is going to be 2 times 4 plus 3, And of course, that's going to be equal to 8 plus 3, which is going to be 11. So, what I have found is that y is equal to 11 when x is equal to negative 2. That's my point, isn't it? If x is negative 2, what's y? 11. G of negative 2 is 11, okay? So I have a point. I have solved for that particular example, okay? Let's see what's g of negative 1 in this same function, okay? The function is g of x is equal to 2x squared plus 3, but what they're saying is what is y when x is equal to negative 1 this time? I'm just going to come in here and plug in negative 1 for x. And I find that that is negative 1 squared, which is 2 times 1. 1 times 1, negative 1 times negative 1 is just a positive 1, plus 3. So what I've got here is 2 plus 3, isn't it? Or 5. So what is my point? What my solution is if x is negative 1, y is 5. So there's my second coordinated point coordinates, okay? Okay, what is the function, what is g of 1/2? In the function g of x is equal to 2x squared plus 3. Well, every time I have an x, I'm going to plug in this time 1/2. Now, I know you don't like fractions, but just bear with me. 1/2 times 1/2, well, 1 times 1 is 1. 2 times 2 is 4. So really that's 2 times 1/4, isn't it? Remember how you would do this. You would act like you would be multiplying two fractions. You're just going to put your whole number over the number 1. And then before you multiply, the best thing to do is cross-reduce, isn't it? Divide both of them by 2. So what do you have? Well, I have 1 times 1/2, which is just 1/2, plus 3, and that's going to be 3.5. So what is g of 1/2? In other words, y is equal to 3.5 when x is equal to 1/2. Those are the 3 points. Let's go ahead and graph this, see what this relation looks like, okay? Or see what this function looks like. The first one is negative 2, positive 11. I'm going to have to go off the chart here to do that one. There's negative 2, 11. The next one is negative 1, positive 5. And then I'm going to have to do 1/2. That's not as hard as it seems. 1/2, just half of 1, right? So 1/2 and 3.5. I'm going to be right in the middle of this right here. So it looks like my function is going to do some curving, doesn't it? But that's as much as I know of it. I can't really graph too much more without doing some other calculations. All right, let's look at this f of x is equal to 6. In other words, the function f of x is equal to 6. In other words, we're saying y is equal to 6. Okay? Okay, when do we plug in y is equal to 6? Well, I know that one, don't you? Y is equal to 6 is going to happen right here, and here, and here, and here, and here, and here. And this looks like it's going to be a horizontal line, doesn't it? That was a little bit, because in my equation part over here, my function doesn't have any unknown x's to substitute in for. F of x is what I substitute in and say y is equal to, and y is equal to 6. So what's f of 1? Well, f of 1, I have no place to substitute anything in except for the other part of the equation. It's equal to 6. F of 0, well, it's equal to 6. F of 171, it's equal to 6. This line is a horizontal line right at y is equal to 6, and that would be that function. It's also written in function notation. It would be f of x equals 6. And that's just a little taste of function notation, and you'll have some more practice with that inside your lab.